Hello, everyone. We're waiting just a little while for people to trickle in now. Welcome to the Whole Tomato Summer CodeFest. We're just going to wait another minute to let people trickle in, and then we'll get started. Thank you for joining us. Just a little bit longer. Still see people coming in. All right, welcome again to the Whole Tomato Summer CodeFest, the C++ coding camp hosted by Whole Tomato. Today we've got an excellent presenter for you, David Millington, and we're going to talk a little bit about that in just a second. And he's going to be presenting Magnificent or Malevolent Maps, Measured, Monitored, and Magnified. And David Millington is the Visual Assist PM, and he's got some excellent content for us today. Today is going to be our last of the series of webinars in our Summer CodeFest, and we saved the best for last. All right, I think people are coming in, so let's go ahead and go to the next slide, David. So before we get started on the actual webinar content, we'd be amiss to not mention Visual Assist. Since this is hosted by Whole Tomato, and Whole Tomato's only product is Visual Assist, we have to talk a little bit about Visual Assist. So Visual Assist is a productivity-focused plugin for Visual Studio 2022. It has many features. Think of it as just IntelliSense, but a superset of it. We've got more, we've got different, and we do things better. We also have more features on top of that. Quite a lot from navigation to refactoring, all your basic needs. And we also work very well and pride ourselves on our performance, particularly in extremely large solutions like, let's say, Unreal Engine 5 and things along those lines. Next slide, please. I'm definitely seeing the attendees still come in. Should hopefully be here, but okay. So we're very well known for navigation, refactoring, code generation. One of our neatest features probably is code inspections, which can rewrite and modernize C++ for you. We have our own parser. It's just such a powerful plugin. There's almost too much to say about it. And that's not really the point of this webinar, but I will say that I suggest you get a 30-day free trial, which is as easy as downloading the product from our website, wholetomato.com, or you can also just search for it in the Visual Studio Extension Manager and download it there. And you just get 30 days right off the bat if you've never used it before, and 7 days on new builds. So give us a shot. I think that you'll find it was worth it. Okay, so as for today's webinar, David Millington, he's the product manager for Whole Tomato, and he's amazing. I'm really excited about this webinar. This is his second webinar in the series today. He's already done one on lambdas, which was excellent and is actually a prerequisite to my webinar. Probably should have come before mine. And today he's going to be talking about maps. So David, I will hand it off to you.
Wonderful. Well, thanks very much, Chris. So today we're going to talk about maps, and I've gone a bit overboard with the M theme in this presentation. Here is our agenda. We're going to look through basically what maps are. Are they as good as they seem? You know, they're a very widely used data structure and one of the key ones provided in the STL. We're going to be looking at different types of maps, the fact that there are more than what the STL provides and how they behave. We're going to actually measure some. We're going to look at some, going to dig into some code that uses them. We'll look in even more detail at a few particular things that come up with some very interesting results. And then we'll have our summary and a live Q&A. So there's quite a lot of content to get through. We do dig into code itself and find some really interesting stuff. So I hope you'll find the presentation interesting. Alrighty. So first up, just a quick summary on what a map are for those who aren't familiar. Maps are a type of associative array. where array is like an array that you're presumably familiar with, or a vector is the most common C++ version. Basically, something that you use array style access for, using the square bracket operator. Associative means that you store a value for a key. Now, if you take a plain old-fashioned array, such as you can see on screen, car R4 equals, and then a few characters, like you can read that by writing car C equals array 0 to get the 0th element. Now, in that, the key is 0, and then the value is what you get, and that's demonstrating associative behavior in the terms of a normal array. Now, look, this is generalized for associative arrays. So you have a map of string and fusel, and that maps, as in correlation, it maps each fusel to a string. So given a name, perhaps, which would be a string, what is the corresponding fusel? And then the source code at the bottom, you can see I've sort of compared 2 lines of code. Fusel F equals my fusels map bar. Now bar is the key. So I'm saying in the fusels map, given the key of bar, what is the associated value, which will be a fusel. And you can see it's conceptually similar to how an array works. Now, there are a few differences. An array has contiguous memory and a map won't. It's one of those kind of data structures where you shouldn't really need to be aware of the internal storage, but it has array access syntax. Now, there'll be some kind of storage behind it, such as a tree or a sparse array or anything really. We'll get onto that later. And there'll be different types of lookup, such as tree navigation or hash for an index into a hash map, or something like that. So those are the main differences. Now, maps are incredibly useful. The reason for this is that the concept of going from a key to a value, of looking something up, that you have something and you want to use it to find something else, is done all the time in programming. You might go from a network name to an IP address, or vice versa, an IP to a DNS. A JSON object is actually a key value pair. You might want to start with a book and look up the author. You have a file name and you want to look up the file. Now, the actual implementation of these might all be very different. They might not use map data structures. A file system is a lot more complex. But conceptually, starting with something and using that thing to find something else is done all the time in development. And that's why maps are very useful data structures. So getting onto general info, there are 2 types of maps, ordered and unordered. Now, ordered are where you iterate through them, begin to end, and you get the results sorted by the key. So if you have 3 entries in your map with keys of 1, 2, and 3, and values of foo, foobar, foobar, and foobar, when you iterate, you'll get them in the order of the keys. That is 1, 2, 3. That's sorted. That's ordered. Now, these are usually backed by a tree, because that makes it easy to implement sorted or comparative insertion and access. If you have a binary tree, then you have a node that either is equal and will contain something, or less than or greater than. And so you can just have very simple comparison operators to navigate down a binary tree to find something. Now, in general, the lookup and insertion in ordered maps is affected by the number of items, so you get an O n log n behavior, but we'll come back to this. An example is stdmap. And then we have unordered maps. And these are where the way something is stored is not based, or rather does not save the order of the keys. So when you iterate them from begin to end, you'll get all the items back, but you'll get them back in any order. Here you can see we get them back in order, with the keys 3, 1, 2, but it could be anything. Now, usually these are implemented by a hash table. So you hash the key, find an index to an internal array, occasionally some other kind of storage, And usually with a hash table, the lookup is not affected by the number of items. I'm hand waving here because there may be storage collisions. But in general, not affected by the number of items. It does require a good hashing function. So it has, in big O notation, O1 access. This is potentially misleading because that 1 can hide a lot, but it will be faster than an ordered map. And an example is std unordered map. And pre-standardization in C++ 11, I think there was a hash map. I can't remember if it was std or that was in boost, so perhaps the slide is incorrect. But before C++ 11, everyone used something called hash map, and then we all switched over to unordered map, which was exactly the same thing. So basically the difference is when you, between ordered and unordered maps, there are differences in implementation, but the differences when using them are the iteration order, whether you get things sorted by key or not when you iterate from begin to end. All right, now std map, which is an ordered map, almost requires a very specific implementation. And it's almost always implemented using a red-black tree, which is a particular type of binary tree. Now, other backends might give different results, and we'll look at that as well. Unordered map requires a good hashing function. In general, your standard library will have good hashes for integers and strings, but of course you have complex types of your own. You might need to handle that differently. But a good hashing function is important to make sure that you don't have too many collisions, meaning that you have a good spread of items inside the unordered map. Now, look, none of this is malevolent exactly. I was just going for M words, but it's more sort of buyer beware or know what you're using or measure. And we're going to dig into this in a lot more detail on the next few slides. But in general, for data storage of any sort, whether you're adding stuff or accessing it or so forth, performance is key. That's one of the reasons we use C++, but even if we didn't, performance would be key. Pardon me. Including common operations like inserting and finding, as well as the worst case scenarios. And we're going to come back to this in quite some detail. All right, before we get to that, let's look at the fact that there are many map implementations. Now, the STL itself comes with 2 std map and std unordered map, as we saw, but there are many map implementations out there in various open source libraries. Now, most of them that I found are unordered maps, and here are a few examples, 7, I think. I went looking even further, and I found 27 commonly used examples of unordered maps with various implementations and various behaviors. 25 of them I found on the website of Martin Leitner Uncle, and we'll come back to this website later, plus a couple of others. Whereas for ordered maps, I actually don't know so many. Abseil has a very famous map implementation. Boost has one. I found a couple of pre-C++ 11 ones, but not many others. And one question for that is why? And likely that's because a data structure where you need a specific order of iteration, ordering by keys, is much less often required than just being able to look up by value. And there's also more variety of flat backends for hash tables than there are different varieties of trees. You have a lot of different commonly used binary trees, red, black, and AVL, and a bunch of others, but there are an almost infinite number of tweaks of hash tables and different behavior. So here's the question, the order of iteration. Most of the time when you use a map, you just add something and then you'll look it up by its key. So how often is it important for you to use a data structure where you iterate from begin to end and the order of what you get is important? You always will get everything in the map, but that the order is important. Whereas effectively just random access is the thing that you need, and the order of iteration is unimportant. The reason this is a good question, and the question I'll actually read it out, how often do you iterate a map versus iterating a list of keys or just doing random access lookup? And how often is the order of what you get back important when you iterate? The reason this is important is that maps that allow you to iterate in a defined order, that is, ordered maps have much worse performance than unordered maps, significantly worse performance. And so if you're using a map without necessarily thinking about the performance or assuming that std map and std unordered map are going to be approximately the same, then asking this question of your code might give you a very easy performance boost. So I just made a claim about the difference between ordered and unordered maps. I said that ordered maps always are slower than unordered maps, and that's quite a claim. And I think we should dig into why I say that. So let's try measuring some maps. So for this presentation, I wrote some code that measured the standard STL maps and unordered maps using 10 million integers. It will store 10 million items. So we'll check 3 different operations. We'll check inserting 10 million integers. We'll read 10 million, but randomly. So we'll have our 10 million, but which ones of the 10 million we'll access randomly. And then we'll erase from the map, and again, randomly. And we're actually going to look at two of the STL maps, map and unordered map. We're also going to look at a tweak for unordered map because it has a reserve method that presets the size ahead of time. And turns out that makes quite a difference. Now I'm using Visual Studio 2019, both 32-bit and 64-bit builds, just the plain default release settings. So, brand new C++ project, don't touch any of the default settings, but I do compile optimized. And also not changing any of the allocators or the hash algorithms or anything. So just using everything default in the STL. And the code on screen just shows a few snippets from this. So on the top left, you can see part of my measure map method. And I'm just using std chrono steady clock to time various operations to get results in milliseconds. And you can see there, for example, that inserting the items, I just use the array access operator. On the top right or the top right hand side, you can see that I'm measuring map, unordered map, and an unordered map with a reserve, but using the same code on them. And look, in terms of using the items, I am creating a list, well, a vector actually, of integers 0 to 10 million, or rather 9,999,999, and then I'm shuffling them randomly, so we get a completely random order. And this is meant to be representative because you often won't know the order of things that you're adding. You really just want to have random access, random addition, whether it's a random key, random reading. Seems a good way to measure maps. And it's a reasonable question to ask what happens if for both ordered and unordered map you use ordered access, such as adding items in order, and we'll actually measure that as well. But in general, just a random access for addition and access and erasure. So 10 million elements. Now all these are measured a few times, rounded to the average 0.1 of a second. And I have 2 tables here, 32-bit and 64-bit. Now the slides are actually available as a handout in the handout section of GoToWebinar if you want to download and look at the table, but I think this is easier to see visually. So I have this chart here. This is the same data as in the previous slide, where you can see that both for 32 and 64-bit, we're measuring the number of seconds it takes to insert, to randomly access, to read, and then to erase items, 10 million at a time. And on the left of each chart is std map, the ordered version. And then the second and third items on each chart are unordered map. And you can see there is a very big performance difference straight up between ordered and unordered. Now, erasing items is the slowest action for all of them. But inserting and reading items from unordered map is significantly faster than for the ordered std map. So for all operations here, std map is terrible. So if we zoom in to see just unordered map, and all these charts are to the same scale, so they're visually comparable. Now, StudMap here is just off the chart, quite literally off the chart, once we zoom in, so that we can see and compare Stud unordered map. We do get slightly different results between 32 and 64-bit. 64-bit is slightly slower, and that often happens actually with all sorts of code. But you can see that the general behavior is consistent. And here we can zoom in and we can see that for unordered map and unordered map with reserve, which I'll get to in a moment, insertion is the slowest. But there is an optimization that we can do, and we can bring down the cost of insertion using the reserve method, and we'll get to that. And random access and erasure are the same. So the takeaway here is that the unordered map is significantly faster than the ordered map. So map is the slowest by far. So what is reserve? Well, when you have a map, reserve, and you might be familiar with this from other standard containers, like vector. Reserve basically tells the container ahead of time how many items it will have in it. So with the plain Stud unordered map, I add 10 million items, one after the other, and it's going to have to do a bunch of work every so often when it runs out of memory to allocate more memory and rehash and reshuffle. Whereas for unordered map, when I reserve it and I tell it ahead of time how many items it's going to contain, it does that work up front before we even add anything. And that way, when you insert items, it really just inserts. It doesn't have to do any other extra work. That's why reserve is faster. All right. Now, one other thing though, everything I've just shown was random order. So I had my 10 million integers and shuffled them randomly so that inserting and accessing them was completely random. But I asked earlier, what happens if we do this in order? So I add integer 0, then I add integer 1, then I add integer 2, and so forth. And when this happens, StudMap actually has very different performance. The insert was comparable to unordered map, and the access and arrays was still slower, but not as much. Now I have a chart for this on the right. Now look, this is slightly different to the previous charts because the previous charts had the x-axis by data type, like StudMap and Stud unordered map, whereas this one has by operation with colors for each type of map. So like compare, each cluster of 3 columns is a set of operations that you really want to compare. So what's most interesting are the first 2 columns in each group. So you can see that map with in-order items, you're adding and you're inserting items in a map, in order 0, 1, 2, 3, and so forth, was a lot faster, about 10 times faster than using a Stud map with random keys. And it was slightly slower than unordered map, but not much. And that behavior, that it wasn't as good as unordered map, but that it was significantly faster than using shuffled keys, was consistent for access and arrays. So why have we seen this behavior? Why is Stud map slow in general, and why is unordered map fast? And then why is Stud map using ordered keys faster than Stud map with random keys? All right, so when you're inserting into an ordered map, it will use a tree, and due to the STL specification, that will use a red-black tree, which is a particular type of binary tree. It's a type of balanced binary tree. Now, a tree allocates memory for nodes. A tree is really good for keeping order because the nodes will be added and the values associated with those nodes simply by comparison. Is a value less than the current node? Well, it goes off to the left. Is a value greater than the current node? It goes off to the right, and so forth. The key here is rebalancing. Rebalancing means that the tree is kept of even depth because you might add something so that you get a really long chain in one part of the tree and a really shallow part of another part of the tree. Balancing keeps everything organized so that in general, the distance from the root node to the leaf nodes is within one node count the same everywhere in the tree. But when you're inserting, in random order, it's going to have a rebalance often, because we'll just get a new key and then it'll add some new nodes, and then it'll realize that it's got out of the constraints that make it a red-black tree as opposed to another type of tree that make it unbalanced, and it'll have to rebalance. That means reordering and shuffling nodes around. They call it rotating, rotating subtrees around. Now, this keeps the tree in very good order, which is one of the constraints that makes this particular type of binary tree fit the red-black tree constraints. But it will happen a lot when you're adding random stuff, because the tree doesn't know what to expect and it'll just get a whole bunch of stuff and sometimes have to reorganize itself. When you're inserting in order, the rebalance won't happen quite so often, though it will happen quite a lot. But it'll also be a lot cheaper when it does happen on average. And we can see that through the speed of insertion. Now, why is StdMap the slowest to read? Well, that's likely because when navigating a tree, you have a lot of memory accesses. So to find an item by a key, you then have to navigate the tree and look up, and you'll go from node to node to node until you find it. And that means that you'll have multiple memory accesses, likely across multiple pages. Cache locality here, where if all the nodes are close to each other in memory or not will affect it, things like that. And slowest arrays, well, erasing will cause a tree rebalance constantly. Now, the ordered item arrays may require less, but tree rebalancing will be a significant issue. Whereas unordered map uses a hash table with buckets. So hash table is basically a large array, and you hash to get an entry into that array, and then you try to put your item in and that particular entry. The question, of course, is what happens if two items have the same index into the array, and that's where Visual Studio's unordered map uses buckets. So each array entry actually has a list that'll have one or two or three items. But in general, it's very fast, because a hash operation, especially over something like an integer, is very fast to do. And that just gives you an array index. And then even you have multiple items there, it's just a quick look. Now, in the case of 10 million items here, the maximum bucket size we saw was 3. So it only had to, in the absolute worst case scenario, we only had to look through 3 items to find the one that we were looking for. So it was a very fast hash, then an array lookup, which is a single memory access, then to find a location, then looking through 3 items. That's not much work. And of course, reserve is faster because it can allocate the entire hash table ahead of time. Whereas when you don't reserve, it has to resize the hash table. And when it does that, has to rehash every entry to make it, to give it a new location in the new resized table as well. And that's why calling reserve is a lot faster. So for interest, unordered map, if you just create an unordered map, Visual Studio 2019's implementation starts with 8 buckets, 8 entries. And after the full insertion, whether you call reserve or not, both have 16 million buckets, 2 to the 24. So effectively, by calling reserve, you're just saving a whole bunch of work ahead of time. And you might wonder what happens in the buckets, because if you have hash collisions, I mentioned that in our 10 million item example, the maximum number of items in each bucket was 3, but the median was 1. So the vast majority of entries, it just looked and it found it straight away. So effectively, this means that the bucket sizes are irrelevant. So if we look at this in big O notation, for a StdMap, insertion is n log n plus rebalancing, which isn't really counted in big O notation, access and erasure are the same. Unordered map insertion is technically constant time plus resizing and rehashing, and access and erasure are the same. Now, when you reserve, you make it constant time, but you don't have the overhead of resizing and rehashing. Now, look, big O notation can be a little misleading sometimes because constant time can actually cover a lot of work. Imagine if you had a bucket and had 10,000 items and then you had to look through all of those. You might try and capture that in big O notation. For most people, write that as constant time because you're writing about the hash lookup, not about the details of what happens there. So you're hand waving here with these kind of things, but as we saw, it actually turns out to be irrelevant, and we can assume it is constant time for unordered maps for insertion, access, and erasure. And if we reserve the space ahead of time, then we avoid the overhead of resizing and rehashing. So this is a long way of saying that unordered map does a lot less work than the ordered map. So hash-based maps, unordered maps, usually have better performance overall. Something I found interesting is that the STL default map by its name is std map. Now, when I started using C++, I learned about things like associative arrays and maps, and I assumed that because one of them was called std map and one of them was called unordered map, that the one I should use is std map because that's the one given the map name. And I assumed that unordered map was a kind of specialized version, and I should only use it if I particularly needed lack of order. And that was an incorrect assumption. Really, std unordered map is the one you probably want to use by default. And personally, I think the std map should be unordered, and we should have std ordered map so that you make a particular choice by name if you actually want order of iteration. However, we don't. It's the other way around. If you make an assumption of which one is the right one to use based on the names, you probably get it wrong, the same way I did years ago. Unordered map is likely the one you want to use, unless, of course, you really want iteration in order. And even in that case, we'll come back. And of course, this is an example of investigating the data structures and having knowledge about your data. My benchmarks here were assuming random access, which is a good generalization. If you happen to know that your data is always going to be in order, for example, then that may allow you to make particular optimizations. So you need to know about the kind of data you're using as well as the behavior of your containers. All right, so let's magnify this a bit. There are more maps than just in the STL. Now, look, the original plan for this talk was that I was going to take 4 or 5 map and hash map implementations, such as the standard ones that I already looked at, and perhaps Abseil and Folly, that's Facebook's one, measure and monitor them, the performance, magnify, look at their features, that kind of thing. So effectively the code that I just showed you, which I wrote, but do this for a lot of different maps and investigate their different performance characteristics. But it turns out that there are an awful lot of map implementations out there, and that other people have done an amazing job of creating an overview. And it's such an amazing job that there was no way I could match it. So instead, I'm going to present those sources to you. Now, the best overview of maps I have seen was by Martin Leitner-Unkerl, and I hope I'm pronouncing their name correctly, at martin.unkerl.com. And they had a post last year, almost exactly a year ago, comprehensive C++ hash map benchmarks. And they had a subline where I spent way too much time creating benchmarks of C++ hash maps, and look at shows. This is an amazing resource. Now, I had read their 2019 analysis, and I hadn't realized there's a 2022 follow-up, and this is well worth reading. I highly recommend this to you, and I will show you the URL to access it again at the end of the talk. Now, it measures almost every possible implementation that's out there. It has a whole bunch of notes on each to help you understand and compare them. It has a table with the maps that are used, with the hash algorithm that's used for various tasks, like your insertion and random insertion and erasure, and benchmarks with integers and strings. I think the reason it's using int and string is because you can rely on your STL for the standard hash algorithm for those. For keys, of course, you might want to use your own structures. I mean, it depends what you have, and you'll need to ensure you use a good hash. But integers and strings are sort of good ways to compare maps. And the kind of results that this website shows are something like this. So a big table, a column on the left of the map type, and then that's subdivided by different hash algorithms. One of them is a standard library hash, and then a few other high performance hashes. And then you get a big table basically of numbers where smaller is better. You can compare the performance for each combination. Now this looks quite dense already as it is. However, this is the actual website. Now that little bit that's highlighted in red right at the top was the previous screenshot. And you can see just how much measurement and comparison this amazing person has done. And you can see why when I read this, I realized that this website is so thorough that trying to do the same thing myself with this presentation would not even nearly match. And as well as all this, it has a discussion of the hash algorithms as well, not just each particular type of tree. And you can use this to find the best container for you to use for your own particular purposes. Now, in terms of recommendations, I mean, this was a huge table. Look, the site doesn't actually give any recommendations and notes that you need to choose based on the performance characteristics that suit you. Look, going into this, I was expecting Abseil to be very good. It has good word of mouth recommendations, but I haven't tested it myself. Look, the benchmark shown here on that page, it was not as high as I'd expected. I was struck by a couple. M-8's hash map seemed overall very good, as does Unkel's unordered dense map, which was written by the author of that webpage. Again, I don't think I should recommend those because you need to go and find, maybe for you insertion speed is the top priority, and doesn't matter how fast you access or how fast you erase, as long as you can insert fast or something like that. Really, or maybe very low memory is important to you. So you really do need to make your own decisions, but those two stood out. Facebook's Folly library is also quite well known, like Abseil, but it had quite high memory usage, which surprised me. Look, one other note is we haven't looked at some things like multi-index tables at all. We just don't have time. But anything complex that wasn't a version of the types of maps that we've seen so far were well down the table in terms of performance characteristics. And it doesn't mean bad. If you need those kind of behaviors, then use them, but it is worth being aware of. There are two main takeaways. First of all of the ordered maps are far too slow. A single ordered map, GTL B-tree map, which is faster than std map, was included in the table just by way of comparison and doesn't do very well. And even that is better than std map. So all of the ordered maps are going to be slower than unordered maps. So back to a few slides ago, almost always the default kind of map that you want to use will be an unordered map. And interestingly, the STL std unordered map, which is the default one, that having realized that unordered is the one that we should be using, we'd normally just go straight to the STL. Look, the performance there can easily be beaten and has been beaten by many other data structures. So if performance is important to you, this points to not using the STL at all. Now look, we haven't looked at the non-simple requirements. Multi-maps where you have multiple values per key or multiple indexes. We also haven't examined different hash algorithms or using different memory allocators. We also haven't looked at keys other than integers, such as complex types of your own or strings. So there's a lot more investigation that could be done, and this really comes back to if performance is important to you, then you really need to measure for your own use case. but I do think that what we have here is representative as a general guide. One question came to mind because I've repeated here a few times that ordered maps where when you iterate between begin and end, you'll get your results back in sorted order by keys because they're stored in sorted order. What if we used an unordered map and then actually kept a separate list of keys and iterated over that to get ordered iterations? So the storage is unordered, but you keep a separate list of keys. Now, this is an example of a common type of optimization that you might implement when you run into this kind of question. You might realize that ordered iteration is important, but you don't want to use an ordered container and then think of some other way to achieve it. And this is an example. So I thought this would be just a really interesting thing to look at for this webinar. There are multiple ways to achieve this. But what I did is I made a vector which copied my shuffled items, and then I sorted it so that I got a sorted list of keys. And then I iterated my unordered map using those sorted keys to get a time. Now, measuring this, I'm counting the time of sorting the keys as part of the cost, which I think is fair. So stdmap accessing, so iterating in order, took about 18 seconds for 10 million items. Now, unordered map accessing, but using my sorted list of keys, sorting the keys, and these are just integers, but hopefully it's still representative, took only about 2.9 seconds. So you're still storing in an unordered map, even if we had to do extra work to iterate in an ordered fashion, was still a lot faster. For 10 million integers, it took a full second on my virtual machine to copy and then sort the keys. Interestingly, it took 1.9 seconds to access, even though random access on the same map just a moment earlier was 1 second. I haven't dug into why, but that's worth noting. But the takeaway here is that tricks like this of just sort of taking a slightly different approach, or you're keeping the same data stored in multiple ways, which is another common thing that people do, or other things like that, can let you take advantage of the characteristics of your containers and the characteristics of your data and the characteristics of how you need to access and use your data. So even doing this, now obviously I use more memory, but even the cost of sorting the keys and then accessing, it was still 6 times faster to keep and sort the keys separately and then iterate my unordered map to iterate in order now, because I'm using by the sorted keys, 6 times faster than using the ordered map. So some takeaways. Yeah, unordered maps a lot faster than ordered. Many people, and I've seen this in general just in code, and I happen to know myself back when I started C++, just used stdmap by default because it looks like the default. And so switching to unordered map will likely improve performance. Now the key here is, of course, if you need iteration order, in which case you might want to keep stdmap, or you might want to use some other technique to ensure that you can iterate in order, because there are bugs that can appear based on iteration order. So there's some straightforward ones. If you iterate your map and then write it to file or something, then obviously if you switch the container, you'll get a different order of the items in your file. That may or may not be important. The more subtle ones, like floating point addition, where you might have the same set of floating point values, but if you add them up in one order, then you'll get a very slightly different result than if you add them in a different order. So you need to be aware of things like that. Also, the hash algorithms are important when using unordered maps. Now these tests just use the STL default stdhash default for integer in Visual C 2019. Look, generally you can assume that the integer and string hashes the STL provides whichever STL you use are good. But of course, you'll need to look at what you do for hashing for your own custom keys. One catch here is that earlier versions of Visual C used an identity hash for integers, and I'm actually not certain when that changed. An identity hash means that when you hash an int, it returns the same int. And that is bad for hashes used in a hash table because it won't give random or even distribution across the table, so you'll get a lot more collisions. So you do need to make sure that the hash you are using is good for this kind of access. And the final takeaway is that there are many maps out there that might be substantially better than what the STL provides. All right. So we'll now have a live Q&A. Please write in the questions panel. We'll be answering questions live. I have some links on screen. There was another useful write-up that I found at kazar.ai, but they generally concluded, if I read it correctly, the STL types are okay, which is completely true. They are okay. Whereas the takeaway that I found is perhaps that there are other types that are more worth looking into. The unordered dense map that looked particularly interesting to me, and this is just personal opinion, so please don't use it in your projects without actually checking it's right for you. There's a link to its GitHub, and that was written by the same person that did that amazing table of comparisons. Also, if you're interested in why a STIB maps tree implementation might have performance characteristics as it does, you can look up Red Black Tree on Wikipedia. It has a good introduction. But really, I think the main link that everyone is going to be looking for is that amazing page, which both had the table and then a whole lot of write-ups on all sorts of things. And that is the link that's in bold at the bottom of the screen. And that sole link, I think, is really the main resource that I would point everyone towards. So thank you. Let's move on to the Q&A now. So Chris,
all
over
right.
to you.
David, that was excellent. And we have some questions coming in. Again, if you've got any questions, please ask them now. This is the proper time. So let's start with a few administrative things. The handout is available in the handouts section, so you'll be able to get all the today's slides. It's a PDF. And if you're interested in seeing this again, which is there's a lot of dense information here, it will be posted to the Whole Tomato YouTube, and there will be a blog about it. It takes us just a little bit to get those blogs out. Someone asked about the session yesterday. Yeah, we haven't posted it yet, but we will. We will be posting these things, so it'll take just a little bit to get these up. All right, so let's on to the questions. Are there differences in memory consumption which may make STD map preferable to unordered map in some scenarios?
Very likely yes, although I didn't measure it. But the reason for that is based on the storage. So it's an excellent question. If you assume that an unordered map uses a hash map, it's going to allocate a big array. So it's going to use a lot of memory. We saw 16 million entries. And then the hash map then will have buckets, which is another potential bit of memory per item. Now that will be a sparse array, so not every entry in the array will actually be used. That's wasted memory. So there may be overhead there. A lot of the hash maps use different types of backing. They might try to have very dense arrays, for example, to save memory, or they might take other approaches. So whereas a tree will actually allocate many nodes, and then those nodes will have values attached, and then you'll probably end up with one node per value, which effectively will be a pointer per value, and that's easier to calculate ahead of time how much memory you'll use. In general, a unordered map is likely to use more memory than an ordered map, very likely. But of course, that extra memory usage comes with the benefit of much faster performance. But check the various different implementations because they all have a whole bunch of different characteristics. That's a generalization that a hash map will use more memory.
Okay, thank you, David. We have a related question. Could you say something about the unused memory space when using unordered maps? In your example, it seems that 10 million elements require over 16 million entries/buckets, of which some contain 2 or 3 elements. Roughly, it seems you need twice the space.
Yeah, look, that's a really good question. So if we have 10 million elements and 16 million entries in the array, that means 6 million entries are actually unused. And of course, some of the entries have multiple items stored in them. So that's a very good observation. And actually, I wish I'd remembered that answering the previous question. And yeah, that unused memory is effectively wasted. Look, what you really want for a hash or a hash table is completely even distribution, so that you have no collisions, meaning that every entry in the table contains 1 or 0 items. And then you want it to be as dense as possible, so there are as few items as possible containing 0. But it's all about trade-offs, and you will get hash collisions. But the choice of hash algorithm will make that more or less likely. And filling something very densely is more hard than filling something sparsely. So the question, if I remember correctly, was, can I say a few words about it? I'm not certain exactly what it is you're seeking, other than, yes, we definitely have to acknowledge that there will be wasted memory. And I would suggest looking at the different types, because different implementations will value different characteristics, such as the amount of memory used. And so if you want an unordered map, but you want low memory usage, there are maps that do implement that.
Awesome, thank you, David. So we talked a lot about libraries. So this person has a question. With so many different maps, how can you be confident on a bug-free implementation of lesser used libraries?
That's a good question. I mean, that perhaps is why we rely on the STL, because we know it works. And in general, I think it would be a result of how many other people are using it and the test coverage for that particular implementation. So if you find a really nice looking map on GitHub and you look for unit tests and there aren't any, it's a bit of a danger sign. A comprehensively tested map is good, and a comprehensively tested map that's used by a reasonable number of people is good. So Folly, for example, which is made by Facebook, we know will be very densely used. Abseil, I think, is related to Google, and so will be very heavily used. And some of these others, like the one on screen, the unordered dense map, I don't know how many people use it, but I believe it has quite good tests. So it probably seems fairly reliable. I think when you get down to it, if you want to be certain, then the STL is the one to go for. But otherwise, you sort of make a trade-off based on how much you believe, based on your testing and usage. You can probably rely on it.
All right, we've got another good question here. So I understand StudMap has better.
Sorry, Chris. If I can answer that in another way.
Go
a
ahead.
long time ago, I wrote an ordered map implementation in a different language. It wasn't C++, using a red-black tree. And I wrote the tree implementation, and I wrote the implementation of the container, that used it and so forth. And I wrote all the tests. And the only user of this particular code was me. And I, after, obviously when writing it, I found bugs, but after the fairly comprehensive testing, it seemed to be all right. And it's now in heavily modified form used in a fairly widely used open source library. And I think that points to it's just an example, but if something is tested well enough and you have enough confidence in it, it's probably okay to use. That was a map used by one person, written by one person, used by one person initially, and it was okay. But sorry, go ahead to the next question, please.
All right, let's go to the next question. Thank you for that. So I understand StudMap has better worst case complexity than unordered map, O log n versus ON. Is this true? And did you take this factor into consideration?
Yes, that is true. And the worst case complexity, if I understand it correctly, I hope I do, is when you have a hash table that you have very uneven distribution within your hash table, and you end up with buckets that contain a lot of items. And so let's suppose you have 1,000 items in your hash table, and 999 of them end up in the same bucket. And so you technically have constant time access, the way you'd normally look at it, which is to find that entry, but then you have 999 of them to look through, and it becomes effectively ON. So yes, that is true. However, in practice, and we saw this in the slides, in practice, the unordered map implementation was good. That was highly dependent on the hash algorithm. So the combination of the unordered map with the specific hash algorithm giving really good distribution meant that wasn't the case. So while true, the takeaway there is to make sure that whatever hash you use gives good distribution with even spread across its values. And there are specific hashes that are often recommended for use for hash tables for this reason.
It's a very good answer, David. Thank you. With unordered maps, should you be reserving a larger size than your data to avoid collisions? And if so, is there a recommendation?
Look, again, this is going to be implementation dependent based on the type of unordered map. But for std unordered map, I would say no, because std unordered map does that itself. So I told std unordered map when I used reserve to expect 10 million elements, and it reserved itself 16 million. So it added in that sort of extra space effectively. Now, I haven't really looked into its behavior for when it reallocates and on what characteristics, but we saw in this test that it definitely had a bit to spare. So I think in general, unless you start seeing really bad performance for some particular reason, you can probably assume that the hash map is looking after that kind of thing itself, at least for the STL implementation.
All right, thank you, David. Another great answer. So we're running close to the top of the hour now, but we're going to finish up with just a few more questions. Thank you all so much. Let's see, I'll choose this one. So I use maps for an entity system to do lookups often. Are there some optimizations there that you might recommend? It's a bit of a general question.
Yeah. I'm most familiar with entity systems as in entity component systems from games, but effectively, if I understand this is where you have a whole bunch of, an entity, you can generalize this to an object, but things that you need to look up often. And look, the best lookup is not to do a lookup at all, even if you have fast lookup in a really good container. So let's take the example of a game, for example. You might have a collection of all your objects representing the player and the trees and monsters and so forth. And you might be looking them up every frame, but you won't be looking all of them up. You will, for example, always be looking up the player. And a really common optimization there is just to look it up once and then store it, cache it. But not even cache, just keep it pointed. So I think the best way to answer that question is, the best lookup is to avoid a lookup. And if you have particular cases or your particular set of entities, and this depends on their relationship, for example, you might want to look at breaking the storage up into different maps based on the type of entity, or caching based on the commonly looked up ones, or even avoiding a lookup entirely when you know that something is going to be required.
All right, thank you, David, and thank you so much, everyone. I think we've reached the top of the hour, so we're going to end the Q&A. I thank you so much for all your questions. We tried to get to as many of them as possible, and thank you for attending the summer event for Whole Tomato, and I hope you enjoyed these webinars. And thank you so much, David, for the work you put in to create 2 of these webinars for us, because they were excellent. These will be available on the Whole Tomato YouTube channel. You will be able to rewatch all of our webinars, and you'll be able to get the copies of the slides. You'll be able to see the slides on our blog. as well as just a general summary of the of all the talks we've had. So thank you so much again. Really appreciated all the people that came and all the questions that were asked. We really enjoyed putting this on for y'all. Any last words, David, before we sign off?
Mostly just to echo you, it's been a great set of talks by a variety of people. I think we had 6 or 7 talks in total, and we really enjoyed having them. And thank you for attending and participating. We hope you found them useful. And really, I mean, Visual Assist is sponsoring this, so we should point out to check out Visual Assist. We're slightly biased because Chris and I work on it, but we do think it's a pretty decent tool.
It is. I would agree. 30-day free trial. There's no harm in giving it a shot. It'll improve your Visual Studio experience. If you code in C++ or C#, just a huge suite of valuable tools. All right, guys. Thank you so much again. And well, we probably will see you again another time, but this has been our summer webinar series. Thank you again and goodbye.
Thanks. Goodbye.